All right. So my office hours will be changing because of the unexpected events that transpired. So it won't affect most of you because most of you don't come and see me on Mondays and Wednesdays. But normally on Monday and Wednesday, I'm in my office from 9 to 11 in the morning. I'm now going to be teaching a class from 9 to 10:40, so I won't have that time slot. And so I've already checked with the chair of the department. He said that that's fine, that I cancel those office hours, and that I am not required to add 2 more hours of office hours. Now, we'll just see how things go, but just so you know, that's official. I'll cancel my appointment things online. I'll try and update the syllabus when I get a chance. But everyone clear on that? Okay. Today, yes. I mean, today, Tuesday, Thursday will be normal. And I might even try and bump it out a little bit further. We'll see. I got to see how this is going to work out. I mean, I'm going to teach from 9 to 3 straight. It's going to be Monday, Wednesday is going to be, I mean, people say, oh, that's like a full, that's a regular day of work. But standing up here, it doesn't seem exhausting maybe, but, 3 1-hour, 40-minute classes back to back to back is a lot to keep your brain focused on. I'm making excuses. Whatever. I'll be all right. So, what are we doing? You want your tests back, or should we wait? We should wait, because then I won't have your attention. We'll wait. I'll pass those back at the end. Just remind me, okay? So I'm actually going to go about today the way that I would have normally started a Cal 2 class in trying to motivate the idea of the integral geometrically. And then we'll see why we did all the techniques of integration, like why it's useful to us. All right? So there's a classic kind of approach to things. Think about back before we had calculators and formulas and all these different things. People were possibly learning that they could live off the land a little bit, and they were trying to create borders between themselves, right? This is my land, this is your land, right? And so you have this need to try and say, all right, that's mine, right? This is yours over here or whatever. And I need to somehow measure how much that is. And so to measure it, rectangles became very easy to measure the area of. We just had a formula for it, right? It was, if this was, let's say, well, I'll say X and Y. This is X and this is Y, then the area here is XY, right? And so for rectangles, very, very simple formula to compute an area. But then the shapes weren't always rectangles, right? So the next classic shape that kind of came into play was the circle, right? So if you have a circle, we all know that the area of a circle is pi r squared. However, that wasn't just known, right? It wasn't on the back of the 10 Commandments. It wasn't a bunch of math formulas back there, right? Or whatever your, whatever your belief is or whatever. I'm not trying to get into religious or philosophical. It's more of a joke, okay? The formula didn't fall out of the sky, right? So where did it come from? So how did they figure out it was pi r squared? Yeah, right? How? So the way they approached it is they said, look, we can approximate this area with the rectangle, or in this case, a square. We could say, all right, I know that that's not a very good drawing. I know the area of that, right? I could go out and measure that out, and I could figure out that area. And then I could, throw another rectangle here in that side and throw another rectangle over here and maybe another rectangle down here and just start filling this thing in with a bunch of rectangles that I can measure, right? And eventually add all these up and you would have an approximation. But that area would actually be less than the true area, right? So you'd be a little bit low here with your estimation because you would have some error, wouldn't you? These little gaps that you didn't measure would be your error. So I'm going to say that this area, I'm going to call it A sub L, meaning that it's a low estimate, okay? The blue here added up, all those rectangles would be a low estimate. Agreed? So then you come around, you say, well, how do I get closer to the true one? Well, instead of doing rectangles inside, you could then come and say, I know the area of this, don't I? This square? Now that area is too much, isn't it? So then I come in here with rectangles and start filling in the outside and start subtracting those from that big one, right? And when I do that, I'm going to get error still, right? There's little gaps in here that I'm not accounting for. Make sense? And that area will actually be too much, wouldn't it? An overestimate. I'll call it A sub U for like an upper bound. And the true area, okay, the true area, which I will call A sub T, is somewhere between those, right? It's bigger than the lower estimate, but it's less than the upper estimate. So what they did is they got more precise measurements, and they got better and better and tried smaller and smaller rectangles and added more and more and more and more of them up. And the more that they did, the closer they squeezed that thing down, right, in between. And they were able to come up with an approximation of what it was. And this method of adding up all these rectangles, this finite number of rectangles, right, there's maybe, say, 10 rectangles in here, or maybe they did 100, or maybe they did 1,000, right? But there was always a finite number of rectangles. They'd add them up. That's called the method of exhaustion, as you might imagine, right? Method of exhaustion, because it's exhausting to have to do this. They didn't have calculators, didn't have computers. So I have another kind of representation of a method of exhaustion with a slightly different approach. Instead of adding up rectangles, right, we can always find the area of a triangle, can't we? Triangle is, it would make sense that we could get a formula for a triangle pretty easily, right? It's not too strange of a shape. So what they would do is they say, okay, I'll take that triangle there. Oh, I will cut this circle into a bunch of triangles like that. I'll find the area of each one of those, and I'll add them up, and that's not going to be enough, right? I have all that yellow error there. But in order to get a better approximation, I go to smaller and smaller triangles. And now I'm going to zoom in, try and zoom in. Trying to see if I can see the error. I may have gone too many. Yeah, well, I can fix it by just. There we go. There you go. You can see the error there now, right? So the more triangles I have, right, the better the approximation. And that's the way it was done for a long time. And then when calculus came around, the approach that Newton took with it was that what would happen if I was able to make the number of triangles in here infinite, right? Then the width of these triangles would actually get smaller and smaller and smaller, right? And if there were infinitely many of them, then it would eventually kind of compress down to just like a single line, wouldn't it? But you can't find the area of a line. It doesn't make sense, right? Lines don't have areas. But the idea of creating an infinite number of them, if you could go to infinity, then you would get closer and closer, and it would converge to the true area, wouldn't it? And we already know that in calculus, we can take limits, we can let things go to infinity, and we can get numerical results, can't we? And that's what happened here. So but it was motivated from the idea of like a circle. All right? Now, what we're going to do is we're going to look at something that's more applicable to what we'll be doing, and that's a function. All right? So let's just I'm taking the function y equals x plus 1, all right, which is just a line, right? If I want to find, imagine that you extend this line between 1 and 5, and I want to try and find the area below this line. We could do this pretty easily with rectangles and triangles, couldn't we? Yes? Like I could just find the area of this rectangle, then I could create a triangle and add those two up, and I'd have the area below that blue curve. Follow me? But instead of approaching it that way, let's try this instead. I'm going to take, let's see, going to create two rectangles there, right? Now the way I'm creating these rectangles is I am picking the left, well, we have the interval 1, 5. I'm cutting it in half, which takes me to 3 in the middle, right? I'm taking the point on the left, which is 1. I'm plugging it into the function, I'm getting 2, right? So the height of this rectangle is 2. And the width of it is what? Is 2 also, right? So the area of that rectangle would be 2 times 2 is 4, right? Then over here, to find the height of this rectangle, what do I do? Plug 3 into the function, right? I get 4. So this height is 4. This width is what? 2 again. So 4 times 2 is 8. Add these up, and you get 12. So my estimated area of this, my estimate, is 12. Now the true area is 16, right? But do you agree that that would work? Yes? As an estimate. Now, how do I get a better estimate? I go and put more triangles in there. So let me put more rectangles, sorry. If I put 4 in there, now how wide is each one of these rectangles? 1, right? Now what's the height here? I plug 1 into the function, right? And I get 2. So that area would be 2. Plug 2 into the function, I get 3. That area would be 3. Then 4, then 5, right? Add them up, and what do you get? 14. So we're getting better, right? And the more rectangles I have, the closer the estimate is. See it right here? 15.1. And it's pretty obvious that I'm converging to 16, right? Does the word converging make sense to you? Going towards it, right? Now, am I ever going to get to 16? No, because there's little errors in all of those, aren't there? There's little tiny errors. You can kind of see them in there, right? So then what we can do, let me back everything back out. I can go to the two rectangles again. But remember how I was picking the point on the left and plugging in, and picking the point on the left and plugging in? Why don't instead I pick the point on the right? That means to estimate this rectangle, I break it up into two rectangles. I have the width of it still 2 here, right? But now instead of plugging in 1, I want to plug in 3. Plug 3 in, I get what? 4? So the height's 4 and the width is 2, so this is 8. And then over here, the width is still 2, but the height here now is 5. Plugged in, you get 6, so 12. Put them together, you get 20. But that's too much, right? So you've got that error right there. The more rectangles I have, though, look at the estimate. It's coming down, right? It's getting closer and closer to 16. So the question becomes, I guess, what would happen if you let the number of rectangles go to infinity? What happens to it, right? Do we get an answer? It looks like we should get closer and closer to 16. Now this is for a line. Oh, I forgot to talk about the middle. Another method is instead of taking the point on the left or the point on the right, I still cut it into two rectangles, but not the left point, not the right point. I take the middle point, plug that in, let that be my height. Notice I have error, I have too much here, right? But then there's an underestimate here, so it's over and under here. That's a better one, right? This one, a little bit over, a little bit under. And what am I at right now? I'm at 16, right? And actually, that gave me 16. Now, the only reason that happened is because of the function, because of the slope of the line. Yeah. So what would happen if I change it? What I'm getting at is that you can look at the left endpoint, you can look at the right endpoint, you can look at the middle. In fact, you can look at any point inside there. It doesn't matter which one you pick, because the more narrow the rectangle gets, it's all becoming the same point anyway. As you go to infinity, as the number of these go to infinity, this width gets smaller and smaller, yes? Okay, now let me throw a different function up here. So there's x squared. And I'm taking the middle point, The true area is 41.3. My estimate right now is 40. As I go and I get more and more rectangles, 41, look, I'm getting there pretty quick, right? Getting close? See? So now, we could, right, I could send you home and I could say, take this function between 1 and 5, create 1,000 rectangles, and estimate the area, right? I mean, I could, and that would be a method of exhaustion. You would be exhausted adding all these things up. So what Newton realized, I guess, is that we could come up with a general formula and then somehow apply limits to these things and see about getting results, all right? Does everyone understand the idea here? Yes? See, there's a log function, another power function. Here's an absolute value function. Cosine, this one's interesting because you get some above and you get some below, right? So I guess you might ask yourself, when you add all these up, this area is considered to be positive area, right? This area would be positive area because the height of the function is positive, right? The height of the function down on the bottom is actually, that's a negative value for f, right? The function, when you plug it in, it gives you a negative value. And if you were to take that negative height and multiply it times width, you would get a negative, wouldn't you? So as we're going to see when we do this, when the function's above the x-axis, we're going to get positive, and when it's below, it's negative. So if you ever put them together, they're going to kind of cancel each other out a little. We'll see it. I just wanted to let you see the different functions. All right? So we are going to talk about what are called Riemann sums. You may have seen this already in Calculus 1. Just depends on your instructor, I guess. Riemann is a mathematician who really kind of spearheaded this whole idea of taking these summations, all right, and trying to add things up. So before I get into the Riemann sums, let's just make sure everyone's clear on notation of things. If you've seen this before, that's the Greek sigma, capital S, right? It's a Greek letter. Now, we use that notation to represent repeated addition. So if I were to want to write, I'll put it below this. Let's say I wanted to write 1 plus 2 plus 3 plus 4 all the way till I got to, like, I don't know, 10,357. I really wouldn't want to write all those out, right? So this right here allows me to write this in a more condensed fashion. So what I do is I write the sigma, and then on the bottom I put what's called the index, the starting index, which I'm going to put here. You can start anywhere you want, but we normally start at either 1 or 0. So this is your starting index. So I'm saying I'm going to start things out by letting k be equal to 1. And then on the top of this sigma notation, I'm going to put where I want k to stop. And I want it to stop at 10,357. So this is your stop. And then in here, next to it, I'm going to put what I want k to actually be. So I want, if I start k at 1, then it's going to cycle, after I let k be 1, it's going to cycle to 2, then 3. So this always goes up by an integer. And so in here, I just need the formula that's going to create this. So I'm just going to put k. So let's see. If k is equal to 1, then I put 1 here. So I get 1. Then I cycle k to 2, right? And I put a plus, because it's sigma means sum. I'm going to add to that now, let k be 2, you get 2. And then I cycle to the next one, put a plus, then 3. Then I cycle to the next one, and then this would keep on going out until I get to the stopping point of 10,357. Y'all seen this before or not? Does that make sense? I don't need the parentheses around the k. I just put it there to kind of foresee. That's almost like the argument of the sigma, but I mean, argument's not really the right word here. All right, what if I wanted to do this? What if I wanted to write 2 plus 4 plus 6 plus all the way out to 50? How could I write that in sigma notation? Sum k equals, you can start it wherever you want. 0, 1, 2, 3, 1. Where do you want me to stop, though? At 50 or at 25? How are you going to create? Those are even numbers, right? How are you going to create the even numbers? Multiply each integer by 2, right? So just put 2k in here. If I put 2k in here, then when k is 1, I get 2. When k is 2, I get 4. When k is 3, I get 6, and so on, right? But I don't stop at 50, because if I stop at 50, I'm going to get 2 times 50, which is 100. I need to stop at 50, so 25. You'll see that? It's a condensed notation. All it is notation. It's just a way of writing out a sum of a bunch of stuff in a nice, tight format. And just make a note here, this is even numbers. This is how you create even numbers. Let me look at a different option. Could I have started this at 0? Okay, how? Because if I plug in 0, I need to get 2. I could do 2k plus 2? No? What would happen if I plug in 0? What would I get? 2. What happens if I plug in 1? 4. Plug in 2, I get 6. Plug in 3, I get 8. So all I did here was I started the index off 1 before, right? I just took 1 index before, and because of that, I had to shift all that by 2. Because if I just put 2k, where would it have started? 0, then 2, 4, 6, 8. I didn't want it to start at 0. I want to start at 2, so I shifted it by 2. Does that make sense? I just added 2 to everything. Where would I stop it, though? 24, right? Because 2 times 24, 48, plus 2 is 50. So there's multiple ways to represent the same thing, right? The notation, the sigma notation for a series of numbers like that is not unique. It can look different. All right, so how about this one? How about if I wanted you to do -8, -6, -4, -2, 0, 2, 4. What if I wanted that? How could you write that? So what are all these numbers? They're all even numbers, right? But some of them are negative. Now, we already know how to make the even numbers, right? I can make 2, 4, 6, 8, 10. I can do that, right? So I know how to make this by starting here. But I want to start back there. So don't I want to just take that and shift it over by how much? What do I have to subtract from 2 to get -8? 10, right? I have to subtract 10 from that. So I would have, what was my formula for the evens? 2k, and then take away 10. K starts at 1 and ends, well, we'll have to figure out where it ends, but does this do it? Plug in 1, you get -8. Plug in 2, you get -6. Plug in 3, do you follow? We're going to do a lot more of this. Chapter 8, sequences and series, we're going to spend a lot of time on this. I just want us to at least get some of the notation and, you know, what it means in our head right now. Where do I stop it? I need this to be a 4, right, at the end? You need that to be 2 times 7, which gives you 14 minus 10. So you need K to stop at 7. Yeah? All right, we could play with this all day long, all right? We could just keep going, keep going, keep going. In fact, we could, if I put at the end of this plus ... okay, like this, that means I don't want you to stop it. I want you to let it go forever. Then you would replace 7 with infinity. Or up there, if I wanted to go forever, I'd replace it with infinity. So you have what's called an infinite series, but we get to that later. All right, so how is this related to what we've done and today in method of exhaustion? Well, the sigma notation gives us a way of adding up a bunch of things, right? And we were talking about the method of exhaustion was adding up a bunch of stuff. So we're going to use this notation when we're trying to come up with a formula for finding this area underneath this curve. So here we go. Let's try this. I'm going to give you just an arbitrary function. There it is. I'm going to cut this function off between 2 endpoints, A and B. I'm not going to tell you what this function is. I'm just going to call it f. So we can't plug in a value. Like we can't plug in something and say, oh, it's spitting out 2 or it's spitting out 5. It's just going to spit out whatever f spits out. Now, I'd like to cut this up into rectangles, right? Yes? Is that okay with you if I cut it? Now, I could cut it into 2 rectangles. I could cut it into 10 rectangles. I could cut it into 100 rectangles. But I want to do something more arbitrary. I just want to cut it into some number of rectangles, but not tell you what it is. So why don't I cut it into n rectangles? Is that okay? So I'm going to cut this. If I cut this into n rectangles, I can't draw all the n rectangles, right? So let me just look at one of them, just one of the rectangles. So I'm going to kind of exaggerate it, that this is one of the rectangles. And remember, I could do left endpoint, right endpoint, or midpoint, or any point, right? For this one, it looks like I did the left endpoint, doesn't it? Now, if I take this rectangle over here and take a look at it, how high, we want to know how high this is, and we want to know how wide this is. All right, so let's start with the width. How wide is that rectangle? We don't know exactly, do we? But we can come up with it. Let me go back to this. This might help. There, that works. So how many rectangles do I have here? 4. How wide is each one? 1. Why? Well, what was A in this problem? 1. What was B in this problem? 5, right? The difference between A and B is 4. How many rectangles did I have in that space of 4? I had 4, right? So each one would have a width of 1. If I cut this into 8 rectangles, right? Each one is how wide? Half, because I had 4, it was 4 wide to begin with, right? And I tried to put 8 into that 4. So 4 divided by 8 would be 1/2. Got it? Yes or no? Yes? So back here, how wide is this? Well, how wide, what's the width here? B minus A, right? B minus A is how much width I have to work with. How many rectangles am I trying to put in there? n. So it's b minus a divided by n. That's how wide this is. B minus A divided by the number of rectangles we have, n. Now, is that how wide each rectangle is? Each one is that wide? Yeah, should be, yeah. I mean, each one of them is the same width, right? So each one should be that wide. Just like in the previous one, each one was 1 wide or each one was 1/2. So as long as I fix my n, it'll be that wide. Now, how tall is it? How tall is it? Well, that's going to depend, isn't it? That's going to depend on exactly where I am here. Yes? But would you agree that if I call some point in here x, I'll call it x bar, or x tilde, sorry. X tilde. It's just some arbitrary point in that rectangle that if I plug that into the function, that would give me a height. I could take the left endpoint, right endpoint, midpoint, any point in there. Since I don't really care what it is, I'll call it x tilde. That fair? Then this would be f of x tilde. That's how high it is. One more thing I want to talk about. Going back to this width. Since this is how wide each one is, right? And it's always the same, right? It's always the same. It's how much width there is to each one of those. Instead of calling it b minus a over n, which I know I could compute, why don't we just call it instead delta x? It's the change in x. It's how much our change in x is. In this direction, left and right, right? It's that change. This width is that change. And then that up there is our f tilde x. That would be the height. So then what's the area? What's the area of this thing in terms of what we have written there? F of x tilde times the change in x. That's the area of that one rectangle, right? Just one rectangle. And what is it that I would need to do in order to figure out the estimated area? I'd have to add up all of them, right? I'd have to add up all of them. So I would do something like this. Now, I'm getting very loose with my notation here, right? Because all I'm trying to do is make a geometric connection to what we've been doing, integrals. So I somehow need to add up all these rectangles, right? So I do some sort of like summation. I start out at maybe like k equals 1 to how many rectangles am I going to have? Like n of them. And I'm going to be, for each one of those, I'm going to say x tilde sub k delta x. Now, why did I put x tilde sub k? Well, if k is 1, right, my x tilde sub k is the x tilde I'm picking somewhere in that first rectangle. That's going to be different than the x tilde in the next rectangle, right? And different than the next x tilde in the next rectangle. That's going to change as I start moving through these sums. So the heights are going to change as I move across. But the widths are always the same, right? Follow that formula? Does that kind of make sense? Okay, now, if I want to not have to do the method of exhaustion and do this, I need to let the number of rectangles go to infinity, don't I? So in other words, I need to figure out what happens when I let n go to infinity. So the next line, or let me put next to this, this is the sum of n rectangles. This is a finite sum, right? It's finite. It's n rectangles I'm adding up. If I want to actually really get the answer, the true answer, I need to let the number of rectangles go to infinity. So what I do is I write limit n goes to infinity of sum k equals 1 to n f x tilde sub k delta x. So I'm letting this number of rectangles go to infinity. This right here is the true area. If you can figure out what it is, but that means you have to add up an infinite number of rectangles, don't you? But that would be the true area, if you could figure it out. if you could compute that. Well, this is a lot to write, isn't it? This is a lot to write. And it turns out that Isaac Newton was able to come up with what's called the fundamental theorem of calculus, right? The fundamental theorem of calculus. And it says that this sum right here, that sum is the integral of f of x dx. But now we're going to attach something onto this we didn't have before, a to b. Remember in all your problems I said if you saw two numbers here, just throw them out, right? Okay. So we started the class off. We said antiderivatives. Oh, whenever I want you to do an antiderivative, I'm going to use this symbol, right? And we found the antiderivatives. What I'm telling you today is that this integral sign is a stretched out S. It's another way of representing an infinite sigma notation. That's what this basically is. The integral sign is what you have when you let that sigma go to infinity. So it's more than just a symbol. It's tied into that symbol also. Do you all see the connection? Do you see that the f of x tilde sub k, do you see that that's this piece right here? Do you see that the delta x is actually our dx? Yes? So if I look at this and I'm a calculus student, what I say to myself is I am taking an infinite sum of the function times the little widths. So I know that these are little rectangles. Does that kind of make sense? The rest of the class, what we're going to be doing is we're going to be trying to attack problems that are geometric, and we will have to come up with the formula. And we will use the fact that this is an infinite sum, and then this part in here, we'll have to figure out what it is, because it just depends on each problem. What is it we're trying to add up? All right, I hope that that kind of makes some sense to you, that this is an infinite sum. Now, I could spend 3 weeks on doing these sums by hand, but we're not going to do that, all right? We're just skipping over it. We're not going to get deep into Riemann sums. I just want you to see the connection between these two notations, all right? So that brings me to the fundamental theorem of calculus. And this is, just so you know what chapter we're in, we're back in chapter 5, actually. 5.4. I'm doing like 5.2, 5.3, and 5.4 all mixed in today's lecture. There's no kind of rhyme or reason here. It's all together. In the future, I may not write fundamental theorem of calculus. I'll just put FTC instead. There are several versions of the fundamental theorem of calculus. They call it the first version and the second version. The second version includes what's called the evaluation theorem, which is what I'm going to give you. All right? Here's what it says. If you have some graph, well, this is what it says geometrically. If you have some graph, and you would like to know the area between the graph of the function and the x-axis, okay? Between the function and y equals 0, basically, then all you have to do is compute this. You take the antiderivative of f of x. Okay, we know how to do the antiderivatives, right? We just spent a lot of time on this. But now we have this little a, b here now. And what that tells us is that, put a space in between there. That tells us that what we need to do is find the antiderivative all right? Remember, if this is little f, the antiderivative is capital F. The fundamental theorem of calculus says if you want that area, you find the antiderivative, and evaluate it at the two endpoints. You evaluate the antiderivative at B, you evaluate the antiderivative at A. That means plug in B to the antiderivative, plug in A to the antiderivative, subtract the two. That numerical answer is that area. It's a way of, well, it's a pretty profound result, actually, right? I mean, you can find the area under a curve as long as you can find its antiderivative. Now, I saved this space in the middle because we have some notation that we use in here to help us keep track of things. When we're actually doing an example by hand, there's this middle step that we do that helps us not forget things. So in here, we like to write, figure out what the antiderivative is, right, just like you did on your test. And then after you figure out what the antiderivative is, you put a line, you put A and B. This just reminds you that you're going to take this, you're going to plug B into it, then you're going to plug A into it and subtract them. All right. This is now called, this right here, is called a definite integral. What did we call them before? Indefinite. Why do you think it's called a definite instead of an indefinite? We're actually going to have what sort of answer here? A finite numerical answer. We should get a numerical answer. That means it's a definite result, right? Earlier when we did the antiderivatives, we got the plus C, remember? And the plus C gave us an entire family of answers. So now we're not saying, oh, it's just all, it could be one of infinitely many functions. It's one numerical answer. And that is all. All right? That's it. That's the big result, fundamental theorem of calculus, the way that I want to present it to you. Since this is the fundamental theorem of calculus, did you know that there's a fundamental theorem of algebra? You ever hear about that? Fundamental theorem of algebra? Like all the major topics in math usually have like a fundamental theorem. And so this is the big one for calculus. For algebra, you're usually not told what it is because it involves complex numbers. But the fundamental theorem of algebra, I'll just put FTA, says that if you have a polynomial, say x to the fourth, doesn't matter what it is. If you have a polynomial equation of degree, in this case degree 4, that you are guaranteed to have 4 complex solutions. Complex meaning you could have real numbers as answers or complex numbers, but you're guaranteed 4. Won't be more than 4, won't be less than 4. It'll be exactly 4. So one good example of this is x squared plus 1 equals 0. There's no real solution to this because when you move the 1 over, you get x squared is -1. We know there's not an answer to that, right? But if you're allowed to use imaginary numbers, then I and -I work. And so there are 2 complex solutions to this. Fundamental theorem of calculus says any polynomial degree n, guaranteed to have n answers. Some of them might be complex. So just in case you'd never heard of that, just want to kind of throw that in there. All right, let's see this in action, all right? Let's see how we're going to use this, because you'll be delighted to know that if you got the integration down, then all we're doing is applying it to this rule to it now. So let's look at that function I had to start with. It was this one, right? And we said that the area under here should be 16. Yes? Let's just verify it with the fundamental theorem of calculus. What's the function we're working on here? X squared, x plus 1, right? What's our interval? What's our AB? 1 and 5? Okay, so I would like to then do the definite integral 1 to 5. We call this number on the bottom, I should probably label this. I didn't, I'll label it on the previous one. The number on the bottom, we call our lower limit of integration. And the one up here we call the what? Upper limit of integration. So you have a lower limit of integration, upper limit of integration, then over here, notice that they stay. And then when you get over here, subtraction, it matters the order, right? So it's always the upper limit plugged in, subtract the lower limit plugged in. All right, so what goes in here for the function that I'm going to integrate? X plus 1, and then dx. And that's probably an integral that you would have hoped all 8 of your problems would have been like that, right? So that's 1/2 x squared plus x from, let's see, 1 and 5, right? So you see how this middle step works? You don't worry about the 1 and 5 here. You just find the antiderivative. You go and do all that work first. Yes? That's right. Now, why? Let's talk about that a little bit. But let me finish this off, and then we'll figure out why we don't need the C. Let's plug 5 in now, right? So I'm going to plug 5 into this first. This is the way I like to do it. I know I'm going to do something minus something, right? It's going to be my capital F of B minus my capital F of A. So I like to separate them with parentheses and subtraction just to keep track of signs and not get all messed up. Okay, plug in 5 into that first. So 5 squared is 25, right, over 2. So 25 over 2 plus 5, right? Which I'll put together in a second. And then I'm going to plug in 1 into this. 1 squared over 2, so 1/2, and then plus 1, right? The reason I didn't put them together first is well, just my personal preference, but whatever you want to do here. Do you want me to put these together first? 2, okay, 35 over 2 minus 3/2, right? So put those together, and that is 32 over 2, which is 16. And that's not a coincidence, that is the truth. Now, getting to the question about C. Had we taken this antiderivative and we had written 1/2 x squared plus x plus c, we would have plugged 5 into that, right? We would have done 1, 5. Would have plugged in 5. We would have got 25/2 plus 5 plus c. And then minus, on the other one, we would have plugged in the 1. It would have been 1/2 plus 1 plus c. And what's going to happen to the c's? They're going to cancel. And that would happen every single time, right? So you're free to put it there, but it's going to go away anyway, so we don't. We just don't even put it there. We good? All right. Now, let's take something like this one. Log x plus 1. Same interval, 1 to 5. So if I'm going to do log x plus 1, this will be integral 1 to 5 log, oh wait, sorry, it's natural log x plus 1. I forget that in Mathematica, they use log for natural log. It's weird, I know. Let me make sure that's the way it is in here. Log, yeah, right there, log. Okay. That's my code. They show it, yes. I have it shown so I can go back up and refer to it if I need to. This one I worked on, though. I won't take full credit for this one. This one was put together by someone, and then I added some stuff in here. I changed some stuff in the code to make it look a certain way for me. But So I don't want to take full credit. This other one I showed you, where was it? This one was all my code. There's not a whole lot of code for that one. That's all mine though. All right. Y'all done with this already? While I was doing it? What are you going to do here? UDU, is that what you said? If you did UDU, what would be? So let's see. How are we going to do this? When we get these, we know that we're going to have to find the antiderivative, right? So a lot of times, what I do is I say, let me just go back, forget that it's a definite integral, and let me just rewrite it as an indefinite, and just work on getting the antiderivative. Once I get that answer, I'll come back to this and plug everything in. So I heard UDU. Is that what I heard? What would U be if you're going to do it that way? Natural log x plus 1. What's du then? 1 over x plus 1 dx. I don't see this up here anywhere. How am I going to rewrite this? You want a u to be the natural log of x plus 1? Oh, the integration by parts. Oh, okay, okay. I'm with you now. Yes, now we could do that. However, I knew what you meant. I was just making sure everyone was on the same page. But I thought you were going to do it this way. I thought you were going to do u is x plus 1, du is dx. If I do that, how can I rewrite the problem? Integral, natural log u, du. And didn't we already do that in class, and I said you could write that down on your formula sheet, or that you should probably remember what the antiderivative natural log of u is? It's u natural log u minus u. Okay, so that's one that we wouldn't have to do the work. The way we did it in class, though, was integration by parts, which I won't show. So this is u natural log u minus u plus c. That's what we did before, right? But now you've got to switch everything back, don't you? You got to get everything back in terms of x. You see why that's so important now? Because where are we going to go with this? We're going to come back up here and we're going to replace x with 1 and x with 5, right? So we don't want to be replacing u with 1 and 5 because that's not the variable. So this becomes x plus 1 natural log x plus 1 minus x plus 1 plus c. And now I'm going to return to the definite integral. This should be equal to x plus 1 natural log x plus 1 minus x plus 1 evaluated at 5 and then subtract being evaluated at 1. We're going to need a calculator if we want a decimal answer. We're going to just do it without a calculator if we want an exact answer. If I want to match up to what the computer is saying, I'm going to need my calculator, right? If I want to get 5.3643, something like that. So let's try this. I'm plugging in two things, right? So I'm going to have this minus, and I'm plugging this. So plug in 5. You should get 6 ln 6 minus 6. Plug in 1, you should get 2 ln 2 minus 2. So this is 6 ln 6 minus 2 ln 2, then what? Minus 4, right? You can put the minus 6 in the minus 2 is plus 2, so that, right? Now, tell me if this is right. Is this ln 6 to the 6th minus ln 2 to the 2 minus 4? Is that the same? Because the power can come up, right? Or the power can come down. And then if you have two logs being subtracted, can't you turn that into one log with division? What's 6 to the 6th power? Someone on their calculator, please. Over 4. What is it? 46,656. 656. The only reason I'm showing this to you is not because, okay, you would need to get it to this, but when you're looking in the back of the book on these answers, sometimes you'll be like, what the hell? And like, that's all that's happening. They're just moving things around, messing with properties of logs. Now, can you do that and tell me what numerical answer you get for this? Okay, and then take natural log. And then subtract 4. 5.364 something. So approximately 5.3643. Exact answer, approximate answer. All right, questions? On homework, I would try and match the back of the book. On a test, I'm looking at the whole problem, so you get to that, I'm happy. But I might tell you, take it to a decimal approximation or something. I usually would specify. All right, we good? Yes? All right. So now, let's return to this idea. What's the area of a circle? Pi squared. Very good. We don't know that, though, right? We don't know that. So here's an approach. Let's try again. Take an arbitrary circle here. I'm going to center it at the origin. I'm going to give it a radius of r. I'd like to know the area. Yes? What is the equation of this circle? What's the equation of it? The equation of a circle centered at the origin, radius r? You're thinking circumference. I'm talking about the equation. Yes. Okay, do y'all remember this formula right here? Well, I don't know. Maybe you do, maybe you don't. That is the general equation of a circle. In pre-cal, this would have been under conic sections. That's the general equation of a circle that's centered at HK with radius r. Every circle in two-dimensional space has that equation where the center is HK and the radius is r. What is h and k here if I put this at the origin? 0, 0. So this just becomes what? X squared plus y squared equals r squared. Now, check this out. I'd like the area of this circle. So I am going to try and find the area of just, well, do I want the top half? No, let me do just the stuff in this first quadrant. Okay, just in the first quadrant. Do you agree if I find that area, I just multiply times 4 and I have the answer? Okay, now the area of that little piece should be the area underneath this curve. Do you agree? What is that curve, though? Well, it's a function. F of x equals something, right? You can get it from the equation here by solving for what? What do I solve this equation for? Which one? X or y? How do we usually write our functions? F of x, right? So we want to solve this for y so that we have a function of x. So solve this for y, and what would you get? Take your x squared to the other side. R squared minus x squared. And then take the square root. When you take the square root, you get plus or minus, right? But does it make sense to you that the positive one gives you the top part of the circle and the negative one gives you the bottom part? So I'm only going to look at the top part, the plus. R squared minus X squared? Yes? Agree? Any questions? This is good stuff right here. What's about to happen. Is that all we need? Can we do it? We have the function, don't we? Do we have an interval? Do we have where we need to look at it between where and where here? 0 and, careful, that's if it was a unit circle. R, right? 0 and R. Because the radius of the circle is R, isn't it? Okay, so between 0 and R? Y'all follow? This stuff makes me happy. I don't know why. It makes me happy. I'm about to show you where the area of the circle formula comes from, and it's just applying stuff that you've already learned. It's a good thing. So I'm going to do my integral from 0 to R. R is a constant, right? I fixed the radius of the circle. Now I want to know the area of it. Now, what's the integral? What goes in here? R square root of R squared minus X squared dx. R is a constant, isn't it? How would you handle this integral? Trig sub, right? Trig sub. What's the trig sub that you would use when you have a constant squared? So that may as well say a squared minus x squared, right? What do you use when you have a squared minus x squared? Is it sine? A sine theta. Now a for us is what? R. So x is going to be r sine theta, right? Dx would be r cosine theta d theta. And then the square root of r squared minus x squared would be a cosine theta, which for us would be r sine cosine theta. Now you rewrite the integral, right? In fact, what I'm doing, I'm going to do this in red because I'm stopping at the definite integral. I'm going to the indefinite right now. This right here becomes integral of what? You have this right here is r cosine theta, and then again, dx, r cosine theta again. So you have r squared cosine squared theta, right? I'm going to put the r squared out here. And I'm going to put cosine squared theta d theta. How do we handle cosine squared theta? Half angle identity, right? So that becomes r squared 1/2. Yeah, we can pull that now. 1/2 1 plus cosine 2 theta d theta. The antiderivative of both of those. What's the antiderivative of 1 with respect to theta? Theta plus 1/2 sine 2 theta. Bam, plus c, right? I'm not going to care about the c though now, because that's coming back up here. Any questions? I mean, this is like a review of integration by parts here, right? Or not integration by parts, techniques of integration. A little bit of a review. Now I need to get everything back in terms of x, right? So what's theta for me? You got to come back up here using the fact that x was r sine theta. Solve for sine theta, take the arc sine on both sides. So this first piece is arc sine of x over r. And then how did we do sine 2 theta? We broke that into 2 sine theta, 2 cosine theta. So this right here really becomes sine theta cosine theta. So we're at 1/2 r squared. Theta we said was arc sine x over r. And then I need to put plus in here What's sine theta? Don't we need a reference triangle here? And cosine theta? I mean, I actually know what sine theta is, but I don't know what cosine theta is. So here's where you would need your reference triangle. Sine theta was x over r. Are you all still there or not? Okay. So this right here, sine theta cosine theta, would be x over r times the square root of r squared minus x squared over r again. I'd like to distribute now the 1/2 r squared through, so I'm going to have my final version of this. Sine theta, cosine theta right there. When I distribute the 1/2 r squared, it's just going to go in front here, and then what's going to happen with the r squared here? Cancel, so I'll just have 1/2 x, and then the rest of that. All right, so next page, I have 1/2 r squared sine, arc sine, x over r, my goodness, plus 1/2 x square root r squared minus x squared. You okay? Plus c. I'll throw the c on it. I don't want to make it feel left out now. Oh. All right, back to the definite integral. Back to the definite integral. I wanted to know what the integral from 0 to r was of the square root of r squared minus x squared dx. That turns out to be 1/2 r squared arc sine of x over r plus 1/2 x square root r squared minus x evaluated 0 and r. You buy that? You don't buy that? Shall we plug in r? Okay. When I plug in r, let's do this one first because this is the easiest one to deal with. When I plug in r for x right here, I get 0. And that kills off this entire thing. It's gone. Now when I plug r in here, I get r over r, which is 1. The arc sine of 1, sine of what gives you 1? 90, pi over 2. Arc sine of 1 is pi over 2. So on your unit circle, right? Where's the y-coordinate 1? Up at pi over 2. So arc sine would be pi over 2. So this right here, arc sine, this whole thing is going to be replaced with pi over 2. But then what do we have in front of it? 1/2 r squared? So I have 1/2 r squared times pi over 2. Well, we have 1/4. Okay, that's what we get when we plug in r. What happens when we plug in 0? Well, let's do this one first. If 0 goes over r, we get 0. What's arc sine of 0? So what angle gives you the y-coordinate of 0? 0, right? So arc sine of 0 is 0. That kills off all of this, right? And now you get what? 0 over here? That's gone, right? It's all gone. So what's our final answer? R squared times pi, so pi r squared over 4. Are we wrong? What's the area of a circle? Pi r squared. But remember, didn't we only do the first quadrant? So don't we still have to multiply that by 4? We're there. Right? Just that one is pi r squared over 4. So obviously all of them together is pretty good, huh? That's what I should do, right? Well, there's actually easier ways to do this. Later on this semester, we'll get into polar coordinates, and we'll do this problem in about 30 seconds. We won't have to do any of the techniques of integration. It'll be a very simple integral, but we're not there yet. So I hope that what I've done today is somehow brought this all together as like, you know, a useful, purposeful reason for it. Now, the area of a circle we all know, but this is the kind of like, if you look back at the way it was thought through, we tried to find areas of certain things. We couldn't really do it. We tried these different things. The calculus came around, gave us a way to do it. But to do this, we had to be able to find an antiderivative, right? And that antiderivative takes a lot of work. I mean, we had to spend 6 weeks learning how to do that, all that integration. So, all right. How about this? Let's say that this is y equals sine x. And I'd like to find the area here and here. So this should be a definite integral, right? I'm going to go, let's try this. Integral, what is the a and the b here for us? 0, and it ends at, pi would be halfway, right? I'm going to go to 2 pi just to start so we can see like what happens if we go to 2 pi. Because remember I did tell you that if it's above the x-axis, it's going to count it as positive, and at the bottom is negative. So this should give us an answer of what? 0, which wouldn't be very helpful, but let's just see that that's what happens. If we go from 0 to 2 pi, and we put in here what? Sine x dx, then the antiderivative here, we don't need to go and do scratch work, right? The antiderivative of sine is negative cosine of x, and we're going to go 0 and 2 pi. When we plug in 2 pi, what's cosine 2 pi? Cosine 2 pi? 1, but then it's negative, so negative 1. And then what's cosine of 0? 1 again, but then negative, so negative 1 there. So that's negative 1 plus 1, which is 0. So that's an important aspect of the definite integral, is that if you have parts of the function that are above the x-axis and parts that are below, then they can kind of cancel each other out, and so your answer may not be helpful or may be off a little bit. So how could I, if I were actually wanting that area as a true area, then how could I do it? Go from 0 to pi instead, right? And then double that answer because it's symmetric. Or I could go from 0, if I was unsure of myself, I could go from 0 to pi, get that answer, then go from pi to 2 pi and get that answer. So let's try this. Let's do the same problem, but let's just do this part here. So your integral changes, 0 to pi instead, still doing sine, arc cosine, geez. Oof, my brain. Negative cosine x is the antiderivative. Plug in pi now. What is cosine of pi? Cosine is the x-coordinate over here at pi. It's negative 1, but then it's negative 1, so it's actually plus 1. And then what's cosine of 0? Cosine of 0 is 1, but then negative, so this will be negative 1 here. So what's 1 minus negative 1? 2. Huh, that's weird. I've always thought it's strange that the area under this first arc of sine is 2. Just seems odd to me that it would be a nice number like that, but it is. Now, what do you think is going to change if I go from pi to 2 pi? Should be negative 2. So we could do that. You can check it for yourself. I won't do it. But if I do pi here and 2 pi here, what changes is that this is going to become a negative 1, and it's going to become a positive 1. So then it's going to be negative 1, take away 1, that's going to be negative 2. Now I want to point out something here that is really kind of fundamentally important, is the way this class is laid out. We started with a little bit of chapter 5, I think we started in 5.5, and then we did all chapter 6. What I'm talking about right now is 5.2, 5.3, and 5.4. So the problems in 5.2, 5.3, and 5.4 that ask you to find these definite integrals assume you have not seen any techniques of integration. So the problems in the book are no challenge at all, because the integration is not a challenge. Does that make sense to you? Which is why there's this debate back and forth of should we do chapter 6 before we do this, and we're not here to debate that. But I just want to point out that because I'm not going to really assign you homework that's going to, like, the integrals are going to be like mind-blowing, you know? The integrals are going to be pretty straightforward. So if they seem that way, it's because of where you are in the book. Make sense? All right. 5, 5. I want to make sure I've talked about everything I wanted to. We're good. We're real good. All right. You want your test back? I'll give you a homework assignment here in a second, but I'll pass your test back first, and while you're looking through your test, I'll put up the homework assignment. Sound good? We might be getting out a little early today. Today? What problem? Bonus on the test? Oh, yeah, that. Well, let me hand it back first, and then everyone will understand. Come up and grab these. I do not believe that these are in any particular order. And the grades are on the bottom right-hand corner. Hope, come grab these. Miguel, Arsha, Miranda, Frank, Emily, Ryan, Rodriguez, Daniel, Reyes, Abraham, Flores, Jaime Ibarra, Kathy, Raymond, Miguel, Miguel Carlos, Stephen, Kevin, Justin, Reagan, Hagan, Dylan, Alyssa, Jeremiah, Nicholas, Richard, Eric, Mike. I'm always open to entertaining any questions you have about the way something was graded, or I'm not known for showing a lot of, like, like why I counted off. Like I just kind of count off. So if you, that's more to make you try and find out what happened. And got something counted off and you have a question about it, then you can get with me and we can talk about why it took off that much or whatever. In reference to the question on the bonus, would you like to see it? Here's the bonus. The bonus was a bit involved. It was integration by parts, letting this be u, dv is dx. And so when you do your voodoo, you go this x times this, you get this rational expression which you have to do long division on first. And then after you do long division on here, you can match, you can do that little trick where you add and subtract something, but you also have to multiply by something. And then I did the add and subtract, and then I split it up, and one of those goes directly. The other one is now completing the square, and then you just got to get all the numbers in order. And anyway, that's why it was a bonus, but it was a bit involved, but it had a bunch of techniques in there. So I believe there are like 2 or 3 students, at least 2 or 3, that did get this, and or got damn close to it. I got a lot of students that got like the first 2. Maybe the third part, but had trouble with the end. But yeah, that was it. Any others you want me to talk about? We've got time. I normally don't provide the answers to you, but I have them all here. So if there's anything you want to see. Here's some homework. And I won't beat you to death with it. All right, we had a good. I already tested you this week, right? You've had enough. But it's just good to practice, all right? I mean, even though the integration is going to be pretty easy, practicing like keeping track of signs and how how the formula works, it's just good to go through all this. Page 289. I'd say if you do 1 through 23, if you do all the odds there, keeping in mind that most of these integrals can be done with relatively simple techniques of integration, all right? Don't overcomplicate it is what I'm saying. I was going to say that, but I didn't want to make everyone upset. I was going to joke around and say, now just go back and do all those problems that had limits of integration. Just go redo them now with the limits. But that would be a great exercise for yourself, you know. Yeah. I'll be honest, a lot of the integration that we're going to do now is going to be relatively easy compared to the integration that we did on the test. It just works out that way. Now, it's not to say we won't face it, but our goal at some point here is going to be to get the integral established. Once we establish what the integral is, we box it up and say we could figure that out later. It's getting the integral is the hard part. I think I did probably talk about it in the beginning of class. You know, we take a function like this. Instead of finding the area, we wrap it around the x-axis. Do you remember me saying this or not? We try and find the volume of that solid if we've wrapped that around the x-axis, right? So what we need to do is come up with an integral that would represent that volume. I'm getting ahead of myself, but I think it's a good exercise just to get our brains going. If I take this rectangle, right, and imagine I just wrap that one rectangle around the x-axis, what would it create? Just the rectangle. It would be like a disk, wouldn't it? A cylinder. What's the volume of a cylinder? Pi r squared times its height. Well, what's the radius of this circle? Well, it's the function's height, isn't it? That's the radius of the circle. What's the height? Well, the height's actually the width, isn't it? How wide is that? Well, how wide is our rectangle? dx, isn't it? dx, this little thing is dx. So this width right here is dx. So the volume of that little sliver then, you mean to tell me, is pi times the radius, which is the function, squared times the height, which was dx? And if you add all those up, right, all of them, then you get the total volume. So our integral is going to go from a to b. Look, I'm going to go through all this again, but I'm just trying to get you to see this. I'm going to go from a to b again. I'm going to add up all those slivers. All those slivers have this format. That makes sense at all or not? So that's my formula. Now that I have my formula, give me a function, I can do it. You want me to get the you want me to get the volume of a sphere? I'll take that red thing that remember that red arc we used just a second ago to get the area? Imagine if I wrap that red arc around the x-axis. Wouldn't I get the right hemisphere of a sphere? So if you go back to the integral we just had, I'm only talking because I still have more time. If we go back to that thing we just had, right, wasn't our integral this one? Right? But now in our new formula, it's pi, right? Pi times the radius squared. Now, this is our radius. Square it, what do you get? I'm pulling the pi out. We went from 0 to r. I square it. Shit, I'm happy about that, right? dx. Check out how easy that integral is. Integrate this with respect to x. What do you get when you integrate that with respect to x? So you get r squared x, right, because r squared is a constant. The antiderivative of x squared is 1/3 x cubed. I'm going to evaluate that from 0 to r. Plug in r right here. You get pi, you got r cubed minus, plug in r right here, 1/3 r cubed. Then you have to take that, subtract. What do you get when you plug in 0 for x? It's all gone, right? What is r cubed minus 1/3 r cubed? 2/3 r cubed times pi. 2/3 r cubed times pi. But that was half. Double that answer, what do you get? 4/3 pi r cubed. That's the volume of a sphere. So I guess getting back to what I was trying to say before I went way off on this tangent is that our struggle is going to be to come up with the formula for the integral. And that will be dictated by what we're trying to figure out. Once we find the formula, it's just integration at that point. And in reality, in a real-world situation, once you establish the integral, you go to Wolfram Alpha and you get it evaluated, right? You do something like that. The challenge is setting it up. So you have to be able to translate what you're trying to do into the math. All right. I'm going to shut this down. I put the homework up there. Try and have a good weekend. We come back. It's going to be back to business. If you want to talk to me, I'm going to my office. We can talk. If you don't want to talk to me, you don't have to.